So here's the deal. We were going to do a double replacement Le Chatelier's principle on equilibrium, but we'll save that for later. What I want to do is go over this, colligative properties. I know you understood when we talked about it before. Remember, you put junk in water, the BP goes up and the FP goes down. But before we get into that, the boiling point and freezing points, I want to get into this first because this plays a part in what we're going to be talking about. Specific heat. And if you remember specific heat, we talked about the specific heat of water. So the specific heat of water equals 4.18 joules per gram degree centigrade. That's a specific heat. It's on your reference table. But my first question I want you to answer is, I want you, question number one, I want you to find the specific heat of aluminum on your phones and make sure there's a whole bunch of different units, but you are going to find the unit of joules per gram degree centigrade. That's the first thing you're going to do, and you're going to write down the specific heat of aluminum. Then you're going to tell me whether aluminum heats up faster and cools down faster than water, or heats up slower and cools down slower than water. That's your first question. So you have to find the specific heat of aluminum, compare it to the specific heat of water, and tell me, how does it compare to water's heating up and cooling down? That's the first question. Okay, we had to move outside because I was getting sick of being inside, and it's a beautiful spring day. Well, let's just say it's a spring day. And water, as we talked about before, has a specific heat of 4.18 joules per gram degree centigrade. That's the highest specific heat of any natural substance. I asked you to find the specific heat of aluminum. You can do that on your phone in joules per gram degree centigrade. Then I want you to compare aluminum specific heat to water specific heat and tell me which one heats up and cools down faster. So as I was telling my mother, who's 90 years old, and remembers World War II, about me making ice cream, that's what this whole lab is about. She said she used to make ice cream in a wooden bucket, but now we use an aluminum bucket. So my next question is this one. I want you to find out the specific heat of wood, and you're going to compare it to the specific heat of aluminum and explain why making ice cream in aluminum would be faster than making ice cream in a wooden barrel. Okay? All right. Now we're going to go back to colligative properties, because all this blends together in making ice cream. Colligative properties, remember what I said? If you put junk in water, the boiling point, you know this, you don't even have to remember, will go up and the freezing point will go down. Everybody got that? Well, ice cream has a lot of stuff in it. And here's the stuff that I used. Here we go. We have heavy cream, we've got regular milk, peanut butter, sugar, we have Hershey's, cocoa, we have vanilla extract, we've got all sorts of stuff, baking chocolate too. So what's going on is we are putting a lot of stuff to make ice cream. And remember, milk is mostly water. So if I put a lot of junk, if we put a lot of junk in water, what will the freezing point actually do? Think about that, because you're going to have to answer that. Okay? So you've got two questions so far. You have the specific heat of aluminum and the specific heat of wood. Why would aluminum be better and quicker in making ice cream than putting it in a wood barrel? All right? That's the first type of question. The second type of question you already know. If I put all that stuff I showed you to make and freeze ice cream, what about the freezing point of this stuff? Would ice be able to freeze this liquid? That is the other question. Would ice be able to freeze it? So what we have is the ice cream mixture with all that stuff I showed you is right in here. And this is of aluminum, not wood. In the old days it was wood. So we're going to put this right in here. And then we're going to put the top on. Okay, so the top's on. This is on. The next thing we have to do is put the ice in here. So once again, the question is, will this ice be able to freeze this ice cream with all the stuff in it? You have to figure that out. Now, the next question is, this is rock salt. And I'm pouring rock salt all over the ice. Okay, so there's salt on the ice. So here's my question. Why did I have to put salt on the ice? I'm going to tell you a story that I told you before that will help you remember. Now, do you remember the story I told you about this bad girl, Nina? Right there. My wife and I were walking the bad one back there. Now back there, right back there, is the town hall. And it snowed about 2 inches. And they salted the road. And we let Nina walk down the road, but she only walked, this bad thing only walked about 10 yards before she left the road and started walking in the snow. And we said, oh my God, Nina, come on, don't be so dumb, walk on the road. Well, the problem was she was smarter than we were because the road was salted. So remember why she got off the road and went and walked into the snow. That's the same idea that's happening here with the salt being on the ice. Now, my assistant right there will start turning this, and she has to turn it for 10 minutes. So,
all right, so I'm gonna sit here.
Yep, she's got to turn that for 10 minutes. And so we'll be back in a short while. Okay, Michelle, 10 minutes is up. I'll do it.
Okay.
You hear the bad dog, so after my 10 minutes, I'll call you back, all right? Okay, so Michelle just got done 10 minutes. It's my turn. She's inside the house. Don't tell her for 10 minutes. We're going to do it this way.
Hey! I didn't know you had an automatic
You
cranker.
weren't supposed to come out for 5 more minutes.
What the heck?
No, don't worry about it. We'll do this a little bit, and then you can come out and crank it again.
Yeah, I
It's good for
don't
your
think
muscles.
so.
So here are the questions that you're going to answer for me. First of all, you write down the specific heat of aluminum, specific heat of wood, which substance would heat up and cool down faster, aluminum or water, and then which substance would heat up and cool down faster, aluminum or wood. So the big question is, so why would the aluminum container be better to use to freeze the ice cream than the wooden container? That's question number 1. Question number 2, will the ice cream be able to freeze with just ice in it? So, will ice be able to freeze the ice cream, just ice? Think about all the stuff that's in there. And your last question you have to answer is, why do I put the salt on the ice? Think about my dog on the salted road, why it ran off the salted road and walked in the snow instead of the salted road. Good luck. Okay, so that is the result, and I'm going to tell you that the chocolate peanut butter is out of control. I wish you could taste it, but hey, you know what? We're going to eat it all in the next couple days. All right, that's how we're going to end the video, right there. So you have to know what salt does. What salt does with ice, right there.